All right, why don't we get started? So Kevin, formerly from Twilio, now working on his own projects, going to talk about where errors come from.
Thank you, Ken. How's everyone doing? Great. Thank you all for coming. I know it's great to have you out here. Thank you to Graham and everyone at Fastly who helped put on the talk. It's great to be here and great to have support from the community. I'm going to be talking about software errors. This talk is more specific, general to programming than it is to Go specifically. But let's get right into it. Oops, I need to refresh this. Okay. If you'd like to follow along, that's my Twitter handle. That's the link to the slides. They're online. There's the relevant Twitter hashtag, which is also being used to tweet about the Giants. So I don't know. We need to figure out something there. But I don't have a better one off the top of my head. So okay. All right. So here's what we're going to be talking about today. Where do errors come from, right? Like where when I write code, errors happen, right? Like where do they happen and when and why and how much? How often do we do it? How costly is it to fix errors, right, at various stages? How much time should I be spending to fixing my errors up front versus fixing them later? How can we catch more of them when we write code? And then if I am spending more of this time up front to sort of on error checking activities, how does that affect my development time? And you might be wondering why I'm an expert in this. I'm really not. I'm an average developer probably, but I can read, and so I've been reading a lot of papers and summarizing a lot of papers. A lot of everything here came from the book Code Complete by Steve McConnell. It's really great. I'd recommend that you take a look at it at least once a year, maybe once every 2 years, because there's a ton of stuff in there. And if you look closely, he backs up basically everything he says with cold hard facts, or not cold hard facts, but at least papers that have been peer-reviewed and people that are trying to study this stuff. I know it's people say, you know, you can't measure lines of code and you can't measure people's productivity, but there are actually academics who have gone out and tried to study these things and say, you know, what do we know? What do we know? What can we say about programming? What can we say about how errors are generated? So there are a few different tools that people use to measure all this stuff. Generally, the activity, the error measuring is at larger companies that have more defined processes and have the sort of budget and the desire to measure their process. So companies like NASA and Raytheon and IBM, and, you know, with very large software organizations, generally that have very high quality requirements. So they'll go around and they'll interview teams, right? And they'll say, what sort of tools do you use to measure quality, right? How do you check errors? What steps are involved before code gets to production? How much time did you spend last week fixing bugs? How much time did you spend in code review? How much time did you spend doing these different things? They also use automated collections, so there might be a tool that goes through and checks the build, right? Or checks every single commit and says, which parts of the code base changed, right? Versus the last time I ran this. And so, yeah, so they might do surveys, right, on every single week. You know, a programmer will get a survey. They might do interviews with specific programmers. And then they try to determine how people are catching errors and where errors are coming from and how many errors are being committed in code. There's a separate technique, which is a little bit more isolated, which is you either give people an assignment, right, like a 5-hour coding exercise, right, or something that should take 5 hours, and then you run it against a fixed set of tests, and you say, okay, how many errors were show up in the original program, right? And then you go back and you say, you either ask people to, you know, write unit tests or code review your test, right, or do pair programming, and then they see how that affects the output of the program, this requirements document that was asked for. Another way to do this is you give people a program that's got a fixed set of errors in it. Say it'll have 15 errors in the program, and then you ask people to find the errors and fix them, right? And then you measure and say how many errors did people actually find when they were using different techniques and that sort of thing. So these are the main sort of methodologies that are used. If you were curious, because I'm going to cite a lot of papers without necessarily going into how those papers generated their results. They're using the techniques that I mentioned here. I also have a lot of these PDFs, but there are lots of them are gated. So if you're interested in getting the hard copy of any of these papers, please email me after the talk, and I'd be happy to send them to you. Okay, so the first thing is to stop using the word bug. The word bug came around because back when a computer was the size of a room, flies would actually get in the computer and gunk up the works. And that's where the word bug came from. It's not very accurate, right? So here are some examples of bugs. If a colony of ants were to make their way into your laptop, that would be a bug. Or if a bird pooped on your computer, or if termites chewed through the server cables outside your data center and cause an outage, those would be bugs, right? Those are random processes. They're basically outside of your control. Maybe call the ant exterminator guy or something. But these are examples of bugs, right? These are random things. We can't really control them, right? Whereas the mistakes that we make every single day when we're writing code, those are not quite bugs, right? They came out of some specific error that we did. Either we didn't understand the requirements, or we typed wrong, or we forgot how the interface worked, or whatever. But the terminology matters. If we call them errors or defects, there's a shift there to just sort of emphasize this is something that we can measure, right? We can measure how many defects we made last week. We can measure how many defects we made on the project. We can correlate the amount of mistakes made with the amount of development time, right? Whereas if we refer to these things as bugs, it seems like there's sort of just some arrow was shot down and caused you to make a mistake, and that's not really quite right. We can actually measure these things and try to get better on them, sort of belying the name engineer, which is in our job descriptions for most of us. All right. So the second thing is admitting that you have sort of room for improvement, and as a developer, it can be tempting to sort of look at errors that you make and say, well, I probably make around 10 errors a day, or whatever it happens to be. Or we ship code to production and it usually has errors, and then we fix it and then we deploy it again and everything's happy again, right? But there is room for improvement in the amount of errors that you make. You have to sort of accept this and be willing to track and be willing to improve. And I'll sort of demonstrate this to you. So here are some studies. Crap. Oh, there you go. Okay. So 50% of the average project time is spent after you deploy, right? Finding errors, refactoring your code, or sort of reworking the code to be more general, or to add new functionality, right? Where this is a really large chunk of time that you can spend, that you can eliminate if you write better code up front. And there are a bunch of different studies that sort of justify that number. The point is, though, if you write better code up front, this is time that you can eliminate, right? And I know we're always looking at how can we build more features and how can we go faster in the amount of time that we have. This is a very good candidate for that, is designing better code up front. And we're going to talk about how you do that in just a sec. So, and speaking of room for improvement, the best estimates that we have are there are 10x differences between professional programmers on all of these different factors: the size of programs that they turn in, the amount of time it takes to complete a program, the amount of errors that programmers make, and the amount of errors people are able to detect when they review code. 10x differences in all of these were measured between programmers, both on large projects and on toy projects. The 10x programmer, right? This, at least in terms of this, not maybe in terms of like your overall job function, in terms of these specific categories is definitely a truth. The other thing that's interesting is it's not correlated with how much experience you have. Generally, these sort of differences persist. It's sort of like teaching, right, where you don't necessarily get better at teaching after your first few years. Programmers tends to be sort of the same. So let's look at some studies that sort of show this. So here's productivity variation between programmers. You can see on the right-hand side we have 20x difference between the most productive programmer and the least productive programmer. On the left side we have 8x difference or 9x difference between the most productive programmer and the least productive programmer. This is on a project with 20,000 lines of code or so, and different features that people were asked to add. Here's the amount of time it took to debug a sample program to find an error in a program. People were presented with a program and said, this has an error. Okay, try to find it. And all these professional programmers went through and said, okay, where's the error? How much time does it take? And so here you can see the results, right? Some people found it inside of between 1 and 5 minutes, and some people took 40 minutes, right? Okay, just one study, but when you start to see more and more evidence like this, it starts to add up. Here's an example of the amount of defects. So they were given a project and saying, okay, please write this, right? And then turn it in, and we'll measure and see how many errors there are. And you can see the people on the left that finished the fastest had half as many defects as the people that took 3 times as long, just based on these error bars, right? And you can see, actually, the people that took the longest had fewer errors as well. But this at least indicates that there's room for improvement for a lot of people, both in terms of how fast you can do something and how few errors you can commit while you're doing it. Okay, so now I'm going to go through and sort of walk you through everything that we know about sort of how these things come about and where we can find them. So 18 to 36% of errors are clerical errors, so typos, fat fingerings, spelling mistakes. Here's an example from code that I wrote at Twilio. This is PHP, and you can see I put $1 in front of a standard library command, which is incorrect. I should have caught that, but I didn't, right? So you can see we have things like this. The 3 most expensive errors of all time involve changing a single character in a program. Just an idea, this is a category of errors, and this is how frequent they are. Most errors are local to a class or a routine, so there's a simple fix involved, which is good, right? This is good to know. Most errors are the programmer's fault. This is a little bit dated, but this is back in the day. You might be tempted to blame the compiler or blame the hardware. Most of the time, it's your fault, like 98 to 99% of the time. Don't go blame the compiler first. It's probably something that you're doing wrong. Other common error sources, so changing requirements. So you go through with a product manager and you get the specification, and then the product manager changes something and you don't know about it, right? Communication breakdown related to the same, either between programmers or between the product manager. This is why Fred Brooks often advocates famously for not adding developers to a project, because you increase the amount of communication that's necessary by the square of the number of people that are involved. And thin domain knowledge. So let's say I go into unfamiliar area of code and I start making changes without understanding the whole program or all of the context. That's a really common place to make changes, or to make errors. Unused variables are also correlated with errors. This is something that Go does really well, is you can't really define unused variables, besides maybe constants in a class, which you can see the constants in the class are not correlated with fault rates, but definitely in routines, unused variables are correlated with errors. So it's probably good that the Go compiler does not let you compile Go programs with unused variables. High numbers of comments. So comments often indicate complex or tricky code. They're correlated with errors, right? And sometimes that might just be that the comments are necessary to explain what is complex, and sometimes it might mean the code you wrote is too complex, and you tried to explain it with a comment rather than work hard to refactor it and make it more simple. Just something to keep in mind the next time you see a section with lots of comments. Complex control flows. So you may have heard of McCabe or cyclomatic complexity. This has to do, it's like a measure of how many branches there are in a function, right? How many different ways, if you start through from the top, you were drawing like a picture of where all the different paths through the code could go. McCabe is a measure that sort of measures this, and what he found is functions with higher complexity measures also had more errors. And there's a program called Go Cyclo on GitHub that can actually measure the McCabe complexity of your code and let you know about where there are things. Errors also increase when you have lots of nesting, right? If you have 3+ layers of nesting, we find that comprehension decreases and errors increase. So try to stick to 3 or fewer layers if you're writing a function. Consider maybe hoisting that out into another function, right? Or something similar, right? Or refactoring your code to not use as many layers of nesting. How are they distributed? So errors follow a power law. 80% of the errors come from 20% of the code. Also, the amount of code changes follow a power law, so generally 20% of the code gets changed 80% of the time. These may be correlated. The idea is you may have hotspots in your code, right? Like spots in your code that generate more errors or correlated with more errors. 50% of errors come from 5% of the code. So one time at IBM, they went through and said, okay, which classes have correlated, which classes have caused errors, right? Or where have errors been in our code in the last year, right, of deployments? They found 31 classes out of 425. They really focused on making those classes, refactoring them, right, to sort of, and improving the quality of those classes. After that, they reduced defects by 90%, public defects and complaints, and they decreased the amount of time it took them to develop new software as well. Okay, how often do we make errors? So if you write 1,000 lines of code, generally you will find between 1 and 25 errors, depending on how good your programming techniques are and depending on how good you are, and depending on how good your review and error checking techniques are. At Microsoft, they found between 10 and 20, between about 1 in every 2,000 lines of shipped Microsoft code had errors in them. So they were pretty good at getting them out before they did it. While you're coding, maybe 5 to 8 defects per hour is a normal number. Okay, how many errors can we expect to find? So there are different techniques. So for any one technique, if you do it well, you can find 70% of errors, right? For the best techniques that we have for finding errors. If we do them poorly, we can find 20%, right? Or if the tool is not very good. There's this really handy chart. Crap. This is going to be hard to see. Oh, man. Okay, there it is. Sorry, this is really small. I didn't have, I'm sorry. Sorry, this is small and hard to read. The idea here is these are sort of the effectiveness of different techniques. On the left are things that are not very effective, and towards the top, towards the bottom are things that are more effective, right? So we have unit tests and regression tests are close to the bottom, while unit tests have a pretty wide spread of effectiveness. But in terms of how effective these things are at finding errors, and what percentage of errors you can expect to find with each of these techniques, you can see there's a pretty wide variance in techniques. Down at the bottom, you might see some new vocabulary, formal design inspections, formal code inspections. We're going to talk about those in just a bit. Finally, at the very bottom, we have high volume beta test with greater than 1,000 users. This is basically we shipped it to prod, and then all the users found the errors for us, which we really want to avoid when we're writing code. Or we want to do all these other things first to try to find it before it goes to production. But just shipping things and having your users find it is a very effective method for finding errors. But maybe not for happiness, but okay. So the interesting thing is that these tools don't really overlap in terms of which errors they catch. And even people, when they use the same techniques, will find different errors in programs, right? People tend to look for and find very specific types of errors, and there isn't a whole lot of overlap here. So inspections, things like code reviews and design inspections, will find different classes of errors than your test will, right? Than any sort of test will, your regression tests, your unit tests. So using different tools can double your effectiveness. Most organizations that catch 99% of errors before they go to production are using 4 or more of these techniques, and almost all of them are using formal code inspections. So there are things like Ken Beck, who preaches extreme programming, right, and pair programming and unit testing and unit tests and regression tests. So it's not so much that that is necessarily the recipe as it is just doing all of those in combination adds up to catching a lot of errors, right? Same at Google. At Google, everyone is required to get a LGTM before they ship code. That's a very effective technique because it requires, a code review and a design review and a formal inspection from someone before any code gets shipped to production. So that's a pretty effective technique, along with their testing suite. Okay, so what the heck is an inspection, right? This is more than a code review. This is a tool by a guy named Michael Fagan, who popularized this from IBM. And he wrote about the success that IBM had in using this technique. It's more formal than just a code review. The idea is we all go into a meeting room and we assign people different roles. We have the author who's responsible for explaining the code and sort of defending the code. We have the moderator who's responsible for speeding things along and making sure that everyone stays interested in what's going on. We can have more than one reviewer. The reviewer is maybe going to use a checklist of things to look at, and they're also going to come prepared for the meeting. They're going to have come to the meeting already reviewing the code, right? And then the scribe. The scribe takes notes on everything. You're not trying to find solutions in this meeting. You're just trying to just find the problems with the code, right? It's not focused on the author. It's focused on the code. You're looking at the code and saying, here are the problems that I have with the code. Here are the things that I found when I was doing my review before I came to this meeting, right? So you come to the meeting. You don't discuss solutions. Management is not present at this meeting. So the technical lead may be present, but the managers are not. Because in the presence of managers, people tend to get blamed instead of code to sort of jockey and make yourself look better. So management is not in the room. It's just the technical team. And then, yeah, as I mentioned, the reviewers have checklists. So the author might say, I want you to look at these things, right? Or here are the hotspots in our code. Here are the things that you need to spend extra time reviewing. How am I doing on time, by the way? Okay, okay, all right. So the thing is, you may have seen from the chart, inspections cross testing on effectiveness. And I was sort of surprised by this. There's a lot of dogma that mentions that testing is really good, and all we sort of need is a lot of code coverage, and our code will be necessarily good. Until I read study after study, and Steve McConnell mentioned study after study in this book, that sort of showed that inspections were both more time efficient and more effective than testing at finding bugs. Errors, excuse me. Oh, okay, great. So reading code, right? This isn't even inspecting. This is just reading through the code, right? This isn't get everybody in a room. This might be a distributed activity if you have a team of people around the country or around the world. Just reading the code found 80% more faults per hour than testing, according to one study. Another study, 6 times as much time to find errors with testing as doing these sort of formal inspections, right? These formal design reviews or formal code inspections. Another test found it was 3.5 hours per error to find errors with inspections, 15 to 25 hours per error when we were doing testing, right? Sort of to catch errors, right? Same for Microsoft. Another study found 1 hour spent on inspections avoided 33 hours of maintenance work. That is to say, if you do the work up front, you can put aside a lot of work in the future, right? Or save yourself a lot of work in the future. So you might be saying, all right, well, why are these things so effective, right? What sort of things do they catch? They might catch, if we do an inspection up front, it might catch a requirements change, right? If we can catch those requirements change and say, wait, the code should be 4 instead of 3, right? We might catch that in an inspection where we might not catch it in a test, right? The test may be totally consistent with the wrong model of the world. If we hard code variable values along the same lines, or if we use magic numbers in our code instead of documenting things and using values, unclear error message, or if we don't have the right error messages, right? If we have typos in our error messages, those sort of things might not be caught by testing, which might just check, did this code throw an error, right? And not, did this code throw the right error? Was this clear to a human? Duplicated code, if we copy and paste, that's not going to be caught by a test necessarily. Inadequate comments, right? For people that are checking the code later. Finally, leaving verbose logging turned on. So let's say I'm printing out, format printf, a bunch of stuff. And that might make it to prod in a test, which isn't testing for, is standard out actually concise, right? These are some examples. There are more. Just of sort of the things that you might not be able to catch when you're just writing tests. But if you are writing tests, here are some guidelines. If you're manually running tests, if you're sort of manually writing code, one estimate was 50% of the time you were running tests manually, you were running them incorrectly, right? Or you're running with the incorrect parameters, or you're passing incorrect data, right? Or you weren't running the right tests. So automate your test scripts, right? Make sure you're automating the work that you're doing on tests. Double check your test code for errors. So a few studies found that people writing tests were more likely to make errors in the tests themselves than they were in the actual code. So that's not great for that. So make sure that when you're doing a code review, you're also checking the test and saying, does this test actually cover the cases that I care about? Finally, make errors really hard to miss, right? So a lot of times when they would do studies like here, there are 15 errors in this program, trying to find as many as you can. A lot of the times the errors were staring people right in the face. They were right in the output of the program, but it just wasn't obvious enough to people that something was breaking, right? So if you make it really, really hard to miss by, like, for example, like exiting the program, right, or panicking when a condition is not hit, maybe you can do this in development and then turn it off in production. That's a really clear sign that something is wrong, right, and something needs to be fixed in your code. What testing is good at? Testing is generally good at control flow issues. So for example, there's a syntax error in a branch of the code that might get missed by a reviewer, but it'll get picked up by a test, which hopefully is covering the different branches of your code. That's generally one of the areas, like control flow issues is what testing is generally good for catching versus inspections, which generally check the interfaces and check the data and that sort of thing. Okay, review small changes. So we might think, oh, this is just a one-line change. You know, can you review this really fast before I ship this to production? And small changes have like a very, very high error rate, right? Because we're not thinking about it as clearly, right? It's like really short falls, like 5-foot falls are the most deadly falls, right? Because you don't think about it, right? If it's a higher fall, you're more careful. So one-line changes can really bite you. So at one company, 55% of one-line changes were incorrect, right? Before they implemented code review and said you have to make changes code reviewed before they get merged, 55% were incorrect, right? So you think, oh, here's the fix. I'm just going to fix this and commit it. You might have forgot a brace, or you might have made a typo or something. After they implemented code review, 2% were incorrect. So basically, the lesson here is you need to take time with every single code review that you do and say, this is a code review and not this is a one-line change, right? This is a significant change. This leading to this quote from Gerald Weinberg says, "Never debug standing up," right? Sit down, think about it, make sure you know what you're doing and you know what you're reviewing. Sorry for the poor quality of this picture, but this is sort of the chance of making an error versus the number of lines that you changed in a pull request, right? And we see here, we got just under 50% for one line, and then this sort of spikes around 5 lines. Like 5 lines, I guess you can do the most damage versus how willing people are to be rigorous when they're reviewing your code. And then it sort of decreases as we add more lines to the pull request, and people say, oh, okay, I really need to check this and make sure it's good. And make sure, too, when you fix things, right, you're not introducing more errors, right? There's sort of a residual rate. Let's say we write it the first time, and we add 8 errors, and then we have to fix 10 lines of code. We might add another error when we do that, right? So we have to be really, really careful when we make changes, make fixes, that we're not adding more errors to the code. I'll give you an example. So I was really big one time on performance. So one thing you can do to avoid reflows is add width and height of images that are in your code. So I made this change to Twilio to the logo, which is on every page. It turns out this is the wrong width of the image of the logo, so it turned out to be a little bit squished. And people got pretty mad at me after that and then said, stop messing around trying to optimize things that you really shouldn't do. So anyway, so one-line changes, like, be really, really careful about them. Requirements change is another source of errors, right? Products change, snowstorms happen, I don't know. Things like software changes all the time, and the thing you're supposed to build is a moving target. It's important to be aware of these sort of changes. I would recommend storing changes in version control instead of something like Google Docs or Microsoft Word, just so everyone sort of knows, like, oh, I last reviewed this document on Friday. What changes have been made to it, right? And Git wikis, like GitHub wikis, are pretty good for this because they actually do have a changelog, and people like product managers can actually know how to edit it without necessarily knowing how Git works. Anyway, just something to keep in mind, that requirements change, and you should be aware of that and careful about it. Keeping records, right? This is really important, right? If you're a company, you want to know, like, you can participate in the science, right? You can sort of work on your own error rate. You can treat this scientifically, and you can look at what you've done and figure out how to make it better. So, for example, you could look at your incident management tool if you have one, or the last 20 emails that have been sent to on-call and say, okay, what classes generated these errors, right? where should we have caught these errors? Were they like errors in the design? Were they errors in just writing the code? Were they errors in the architecture? Were they misimplemented requirements, right? And then just see where these sort of errors are coming from, right? How are these things getting to production? How are these things causing the pagers to go off and customers to be upset, right? You can do this as a company, right? You can say, how many build failures do I have? When I hit go build, right? How many times did that fail versus how many times did it succeed? You can add some kind of hook that sort of makes this happen. Just keeping those errors, right? And then you can measure it over time and say, well, am I getting better? Am I getting worse? Do we consistently have a problem in this class, or do we consistently have a problem in this phase of the process, right? We can sort of do that. Here are some things you can measure. The number of errors detected by the compiler, the number of failed builds, the total number of defects in your code, right, after it's been shipped to production for 6 months or a year. How many defects were there in this feature, right? How much time, how many hours after it's shipped to production did I spend working on this, right? What is the severity of the defect, right? How many times did I cause like a production outage, right? Versus how many times did I inconvenience a customer or inconvenience someone who was trying to deploy but couldn't because I broke the build? Which classes cause defects, right? Which classes are associated with a high number of defects? I just mentioned, what is the origin of the defect, right? Is it just writing the code? Is it in the design? Is it in the requirements? Is it in the architecture, right? Where did the defect come from? And then sort of cost to correct it, right? You can measure this in terms of customer lost billing hours or software engineering hours. Google, actually, I know, converts everything into software engineering hours, including like hours of time on the server, so they sort of use that as their like standard measurement for everything. They figured out a way to compute this and then sort of use that, right? So we can measure this, right, is the idea. And then when we sort of find something, hopefully it's a good measure and we can use it and help us get better at writing code, right? When we measure things, we can at least track them and say, we're getting better, we're getting worse, right? Here's some steps we can take. Here are some steps I thought of that can help us, get this error rate down. So here's some sort of estimates of the cost of fixing things at various stages in the process. So if you add some requirements, right, and then someone goes and writes the code, and then you say, oh wait, we actually need to do something totally different. It's generally 5 to 10 times as expensive to fix once you've started writing that code, right? You need to go find someone and get them to change it, and they need to load a new mental model in their head or maybe redo the architecture. So getting the requirements right up front is really, really important, right? Making sure you understand what's going on. Same with an architecture defect, right? If we build the wrong architecture, right, or sort of use the wrong data structure, or use the wrong database, or don't understand the requirements, that can be really, really expensive. After it's been released, if you need to fix code after it's been released, 10 to 25 times as expensive as before you release it, right? In terms of the cost to customers, in terms of the cost of loading that code back into your head, of context switching from the new thing you're working on to the thing you're working on that broke last week. The requirements, architecture changes are 10 to 100 times as expensive to fix. And there are a few different studies that sort of try to measure this based on statistics from a number of large companies. So here's something I did. This is a spreadsheet from 1 month of pull requests that I made. And I just tracked and said, OK, how big was the diff? How complex was this code? I just assigned a complexity level to it. Where did it have a bug, an error, excuse me? If it did have an error, where do we catch it? And then why did it happen, right? And then I was able to use this and say, OK, I really need to be more careful with this and with this and with this. I'd really recommend this, right? And this isn't that hard to automate if you have something like GitHub where they have a really nice API. You can go through and sort of measure your code and just annotate the parts that you need, which it shouldn't actually take that long. OK, that's it. That's all I've really got. You can find the slides online. Again, email me if you want to look at any of the studies. And you don't have access to something like ACM or IEEE membership, and you don't want to pay $30 for all these PDFs. I'm working on a new project called 20 milliseconds. If you go to 20milliseconds.net, you can find what I'm working on right now. It's not related to Go or errors at all, but I thought you might want to check it out. Thanks for listening. This is the first time I've given this talk in public, so if you have any feedback for me, please let me know. I'd love to hear it. Thanks very much. Are there any questions? Yeah. Yes. That's a good question. So generally for an informal review, the author is driving the sort of walkthrough of the code. Maybe it's from having a moderator who's sort of looking at things, right? From having individual reviewers who have all reviewed the code independently and then brought that to the review, right? Brought that to the discussion. So you can sort of get this right when you just read through the code independently, right? I guess sort of the collaboration between the people in the room, right, and sort of the bouncing ideas off each other is pretty important. But I'd have to go through and look at the sort of papers more specifically to give you a better answer to that question. I hope that helps. I can point you to the right spots in Code Complete where they have more full discussions of this if you want after this. Yeah. Uh-huh. That's a good question. Right. It's probably easier to deploy, right? So sort of changes are bad for less time. You can still sort of think about costs in terms of customer costs, right? Like when we ship bad code, it has a cost in terms of the number of customers, effects, and everything. The context switches are still, there's still a cost. I'd guess this would have decreased by a little bit, but I'm not sure how much. It would be good actually to see. I'm sure there are newer studies. I just don't have them right now. The library books are on their way to San Francisco right now to review the answers to those questions, but I don't have them right now. So that's a great question, though, and I don't know the answer to that. Yeah. They're just building completely the wrong thing, right? It's still a big problem. Yeah. That is a good question. I guess the question was how do I sort of do code review when I'm working by myself? It's tricky, right? You try to prioritize and ask people for suggestions and advice where you can. Generally for the larger things like which language should I be using, what framework should I be using, I'll definitely try to consult with friends before that and sort of get their feedback. A lot of times I try to use open source libraries, right? I try to use other people's code. I mean, I don't have great answers for you, but yeah, I don't really know. Besides, I try to publish things I work on too and make sure they're of high quality and good enough to be used, by other people, and that I'm documenting it and sort of writing it for other people. But yeah, it's really tricky to do. In terms of open source, yeah, it's definitely good to try to get someone on your side right before you go in and open a pull request, right? Talk to a contributor on the project and say, hey, I want to make this change. What do you think about this? Have you tried to do this before? Would you be open to reviewing this? Can I review some code for you, right? Because as we saw, a lot of the drivers of sort of good code are having it get reviewed by someone, right? Or having someone there who's sort of can look over your code and say, is this good or not? And ultimately, that contributor to the project is going to have to merge your work, right? So you sort of have to, it's good to go up front and say, hey, what do you think about this? Would you be open to this? It's my proposed design good enough, for you, and then hopefully they'll be more amenable when that pull request comes into the project. I hope that's not a great answer, but yeah. Oh, great. Are there any other questions? Kyle, did you have oh, sorry, yeah. One second. Yes. What? Oh. What? Oh, I don't know. I make lots of mistakes. Pretty average programmer, as I said. Probably. You can ask Kyle or Alan Shreve after the talk if you want. Yeah.
One thing I found interesting that this suggests
That's a good question, right? I mean, it's sort of everyone has to drive it, right? I guess to fall on the technical lead really to sort of enforce high quality and sort of make sure everyone on the team is committing code that's up to a good standard, right? And sort of enforce the procedures that are there, right? Hopefully teams have a technical lead. And oh. I mean, I guess people in general, like product managers and management teams, tend to emphasize feature development over, code quality, just because that's what they can see, right? They can see a new feature on the website or in the API, and they can't really see the rotting hulk that underpins it, or the sort of the effects of writing bad code and sort of the discipline, right? Like the speed that you can get from being disciplined about writing good code up front. It's sort of harder to see, right? So there's this really great graph. I should have put it in here, but it's like the amount of time spent on a computer, and it's from like 1960 or something, and like all through like the design and requirements phase, like it's like really, really like close to zero, right? And then it sort of goes up as you get to sort of writing code and testing, but it's like really way down. Like you shouldn't be on your computer when you're sort of designing things and sort of inspecting them and figuring out what code to write. Anyway, this is kind of a useful thing. Thank you. That's a good question. That sounds pretty great. The idea was just put up a video board that's got stats on failed builds and failed releases and tie product managers to that effectiveness, and then maybe they'll listen a little more. Okay, thank you very much, everyone. I had a really great time talking to all of you.
Hi, everybody. I'm Adam Thomason. I work here at Fastly, and we are a CDN, and we like to think of ourselves as next generation CDN, and what that means is that a lot of the things that you couldn't classically do with the CDN, like very fast invalidation or high throughput invalidation or getting logs about what the CDN is doing on your behalf, getting that stuff out in real time is really what we focus on. And we're hiring, and the team that I work on is responsible for a lot of the glue systems and the control plane, and the majority of projects that we've started in the past year have been in Go, so we like it. So today I'm going to talk about a lesson that I took from the first Go project that we took on here. Which was the first non-toy project that I built in Go. And so this is kind of a way of don't do what I did. And so the topic here is about the similarities and differences between strings and byte slices in Go. So to start with, let's do a quick recap of what they are. So strings and byte slices, those are two square braces, they don't really look like it, are very similar. So they're both views of a piece of memory, and the data structures themselves are represented by the current version of the reflect package. They're both headers. They have a pointer to the backing array, and then a length of how many bytes are in that array. The slice additionally has a capacity so that the slice can be resized over time, and the slices can be changed. One of the main language differences between these two things is that strings are read-only. You can access a byte of a string with typical C-style array syntax, but it won't let you change anything there. You can go through unsafe and monkey with it, but generally not a good idea. So these two things are really easily convertible between each other. So a lot of times it can be easy to not think about the differences between them, because if you need one and you have the other, just convert between them. But quickly about strings, this catches a lot of people. Strings are not Unicode or UTF-8, they are just binary data. String literals that are in Go source are by definition UTF-8, but these are different things, but just keep that in mind. But strings can have any arbitrary byte data in them. Strings are really tempting to use anywhere you can for a number of reasons. The syntax is a lot nicer in a lot of cases. You have to use append with slices, and using the ellipses and various stances there can become quite a pain. Strings, you can just add stuff together. Because the string header is 1 int smaller than the slice, copying strings is a fair bit faster. Like byte slices, strings can have arbitrary data again. The compiler can make certain assumptions about a string because it knows that the underlying data is not going to be changed out from underneath it. And a ton of stuff implements the fump.stringer interface, which gives you a string. So you get strings from a lot of places. So why would you use byte slices instead? Really because there's a lot of stuff that does, especially anything I/O oriented. Everything in package I/O except the write string helper function operates on byte slices. The ubiquitous reader and writer interfaces from I/O all do bytes. And standard library just in general uses lots of byte slices. Going back and forth between these is really easy, and fundamentally it's just a copy of the backing array for both of these things. The syntax, you just put the thing you want and then parentheses and the thing you have, and boom, you've got the other side of it. So what happens when you start doing these casts? So say you have a function that takes an I/O writer and you want to write something to that I/O writer, but the thing you started with was a string. So you cast to the slice and pass it and everything just works and you go on with your day. Yep, it worked. The issue here is that the compiler usually has to copy the data. Even if the thing that you're passing it to doesn't care about it being writable, the compiler has to go through a lot of gymnastics to be able to tell if the entire call chain that you go through never makes any changes to the argument, and only then can it actually make that optimization, but typically it can't. And in a case like this, where you're passing the byte slice outside of the function, the escape analysis says that this thing now has to live on the heap. So you've copied a thing which take time, and you've created garbage that has to get cleaned up later. So if you're doing things in a high throughput environment, this can pretty quickly add up. So to start with, this is the motivating example of the thing that I started with at Fastly, which is fundamentally a demuxer. So we have a string of inputs. So we have log files generated by Varnish, which is the caching server that we use. And we have to look at these lines, figure out which service which is associated with a particular customer, and which logging endpoint that they've configured do we actually want to send this line to. So the fundamental operation of this program is keep reading from this pipe, and with every line that we see delimited by a new line character, do some analysis of the contents of this line, and then send it somewhere. So structurally, a very simple thing here. We just start off with a channel because we want to have a bunch of workers all doing this in parallel. So we start up workers. There'd be more than one here. But what each one does, it waits on the channel to get the next record. In this case, we're going to start off with a string. And then look at the string, find the information about what the destination is, get or create a connection to an outgoing endpoint, and then write it to that endpoint. And we just do this over and over again. So what sort of thing would make sense to use for this kind of read loop? And we go and look at the standard library buff.io package, and it has something that looks really promising. Scanner provides a convenient interface for reading data, such as a file of new line delimited lines of text. Sounds perfect. Now, if any of you watched Brad Fitz's talk from GopherCon, he mentions offhand that there are hardly any uses of Scanner in the standard library. It's got some restrictions that they're documented, but they're not boldly advertised. One of the main ones is it can only operate on a maximum line length, but there are some things that, as we'll see, you may not want to do with it. So the first problem here is we're calling text. So down here, sorry, need a real pointer. So if you look at the documentation for the text method of the scanner, it allocates a newly allocated string holding its bytes. It has to. It's operating on a byte stream, which is coming from a reader, which operates on byte slices. So in order to give you a string, it has to copy it. And looking at the other end in the worker code, because we had a string and we wanted to write to something that operated on a writer, we needed to use the IO write string helper method, which under the hood, unless it's the output that you're writing to has a special consideration, has to copy it just back to a byte slice. So you've got the copy and the garbage problem. So maybe scanner text is not what we want to use here. In contrast, scanner.bytes does no allocation. All it does is takes the input stream that it was looking at and gives you the slice corresponding to the start and end of the record, delimited by the new line, which is scanner's default. So let's try using that instead. Everything looks almost the same. The difference is that the chan is now of byte slices, and we don't have to call write string anymore. Just call con.write because that implements, so in our case in the log dispatcher, that's operating on TCP cons, and you can just write your byte data. There's a problem here though. Because this is happening asynchronously, by the time that the worker gets around to trying to write the data here, the underlying thing that came from the scanner will have changed. So you'll go about and start writing junk to the wrong spot, and that's not a good thing. So fundamentally, you need to make a copy here. But if you do it yourself, you can be smarter rather than just letting the scanner and its text method make a string. So this should say pool of bytes. The recommended way that pools were implemented up until the Go 1.3 was have a channel of whatever object that you need to have a pool of. When you get one, if you can read off that channel and it's buffered to some amount, then you just use that one. If you can't, in the default case, you just return it a new one, and then to release something that you've already gotten from the pool, you just put it back. Similar default case of the channel write, just throws it away. You let the garbage collector deal with it. Now, in Go 1.3, there is a sync.pool, which is a runtime mediated way of doing this, and it's got some smarts under the hood, so I would recommend doing that instead. So that's a reason not to go back and forth between these. When would you? So, a common case of something you might want to do if you're reading data off of a stream, like in the previous case. So for instance, when we needed to do getCon on dest. So we need to look up in some sort of map, usually, is what you're going to use in Go, and you need to have a key to that map. So in the string case, we still have this copy, but it works as expected. But again, copy, sad. Is there anything we can do? We saw scanner text is maybe not the best idea in general. What else? How about the bytes idea? Well, so now you're going to need to have a map whose key is a byte slice. You can't do that. So map keys are only defined on things that have equals equality. So if two things can be exactly compared, then you can use them as keys. This extends to structs, chans, lots of stuff you might not think. There's really not a lot of reason to have nested maps in most cases because you can have pretty complex keys. But you can't have a slice. So what do? Well, we need to go back to the map of strings to whatever. And here, we have the copy, and it works again. But here we've done the cast inside of the map access. It used to be no better than the naive way of doing this up front. But as of the latest revision, this is actually fast. Under the hood, what the runtime is doing is just creating a fake string header associated with the byte slice because it knows how long the thing is, and it can actually compare the binary data pretty trivially. So this is all just hidden away in the runtime, and it works. It's sort of weird that if you were to break out the string data into a separate variable, this optimization no longer applies. And that's why it didn't get merged for a long time, but now it works, and it's awesome. So in short, whatever APIs you're using, if you're dealing with format package a lot, you're dealing with strings. Stick with strings as long as you can. If you're doing I/O, use byte slices because you'd rather not convert between them. The copies that things make is pretty well documented in the standard library. The rule of thumb with Go is that the docs are not verbose. They say the exact right thing in one place, so you better have read it. Know where your copies are. In your own code, know what is making an allocation, what is copying after that allocation, and what things are getting passed to other functions or returned from your functions, because that will create garbage, and you'd like to know. So how do you know without just scrutinizing every line of code? A great thing for that is the benchmarking facility in the testing package. You can turn on allocation reporting, and during each iteration of the benchmark, it will count against the runtime stats of how many allocs it had before and after. And so you can see, just like this here, this is how I did this, you can see if things are making more allocations than you expect they ought to be. In production, the runtime module has a lot of statistics on what allocations are happening. And the pprof facility is fantastic if you look at the graphs or the output of top from the tool. You'll see some runtime functions that are associated with copies and allocations and the garbage collector. And so you can see when this stuff is happening pretty easily. And there's a bunch of stuff on the Go blog about the details of how these things work externally and internally. They're all really good reads. That's all I got. Thanks. Any questions? Eric? She's sad. She had some knee surgery, but she's better now. Yeah.
The example you showed, I don't know how real it is, but it's a pretty common thing to have a problem when parsing lines and text are coming in, parsing them through like a field. Do you have practical experience to say that writing your code such that that buffer of data being represented as a string is not that much more difficult to process than represented as a byte? A lot of libraries might be built like a regex library, maybe built to work on string.
Yeah.
Byte slice, those are really practical problems. Operating on byte slice doing that kind of line.
So my motivating experience here is mostly on taking stuff in from the network, putting it out on the network, and just kind of massive copy operations. In cases where you only have a single choice in an API, I think it's generally better to just bite the bullet and do it. There are a lot of duplicated APIs, though. So the bytes package and the strings package have a lot of extremely similar identical methods. So use the both of those with whatever data you have. Yeah.
As you showed with the casting of the string inside the map, is there any performance benefits then by pulling the string out of the map using key?
The reason that this got merged, again, Brad Fitz is the guy who does a lot of the standard library stuff. There's a bit in the HTTP package where it canonicalizes the headers. So you want to be able to get out what is the header for a particular thing. And so HTTP is reading stuff off the network. It's dealing with byte slices. So what it does is it builds the map of the string to itself. And then so you can get out the string for further processing down the road without having to do the key copy up front. So that's one trick that might be helpful. Yep.
What led you to decide that this was an area you wanted to optimize on? Like, what were you looking at that gave you the indication that strings and license copies were
A combination of two things. The most severe one was the ganglia monitoring that we have of all of our production daemons, and noticing the amount of GC time creeping up pretty severely over time to be sometimes greater than 15%. And there's really no excuse for that because, again, you're making a copy just to somewhere down the road make a copy back. And you may have to work a little harder to stop that from happening. Again, like if you need to make a copy of your thing because the input data that you have is going away before you have a chance to operate on it, then you need to store that somewhere. But pools will let you largely do that without all of the GC pressure. Anybody else? All right, thanks very much, guys.